All right, guys, so welcome to the second half of Unit 4. We're going to get started looking at some of the properties of integrals that we can use that are very helpful and applicable. One of those, one of the big ones, is we can use integrals to find area under curves. And so we are going to talk about that as in terms of the definite integral. Definite versus indefinite. Last unit we were doing indefinite. Now we're defining where that interval starts and stops. So for example, on the interval a to b, we're going to write our integral, but now we'll say from a to b. So notice little a to b here, and then our f of x dx. So again, what this is going to refer to is the area under our curve. And when our area is above the x-axis, it's a positive value. When it's below, it's negative, and so on and so forth. Okay, so some of the ways that we find those sums are something called Riemann sums. And the primary ones that we end up using are something called the left-hand rule, the right-hand rule, and the midpoint sum. And what that really does, guys, is this. It draws little rectangles from the x-axis up to where those rectangles would hit your curve. And so for this one, I'm using the left side of my rectangle as the height. And then I've got this one, then I've got this one. And so what you'll notice is when I create these rectangles, I get close to what the area is under the curve. Now, obviously that's not perfect, but imagine, we're going to do this in the future, imagine that we could let these rectangles have widths that get smaller and smaller and smaller so they would fit perfectly under the curve. And obviously we've dealt with things before where they get smaller and smaller and smaller with limits. So we're going to kind of bring all this together later. For now, we're just going to practice doing these. For the right-hand rule, we use the right side of our rectangle to define the height of our rectangle. So here I go, notice here's my second one in there. And so then this one on the right-hand rule for this particular graph, you'll notice I'm a little over what the area is, but that's okay. It's not always the case that the right-hand rule is an overestimate, and it's not always the case that a left-hand is an underestimate. Depends on the way your curve is facing. And then there's something called the midpoint rule, which gets even a little closer because as you can see here, I'm a little above, a little over, and then a little under. And the midpoint rule, same idea. You go midway between your little intervals, and I find that as the height of my rectangle. So those are our three main rules we're going to look at today. There is another one. It's called the trapezoid rule, and it's when you connect it and use the trapezoids, areas of trapezoids instead of rectangles. Now remember, area for a trapezoid is 1/2 the height of the trapezoid times the average of the bases. Now, typically, we think of trapezoids as setting on their bases and then having a height, something like this, right? And so here's your base 1, here's your base 2. For these guys, though, notice this distance here in between is actually the height of the rectangle, and these two guys are the bases. So that's just something to keep in mind. All right, so let's take a look at some examples. So in this first one, notice we're saying estimate. Basically, remember, this means I want the area under the curve from 1 to 4. So here, notice I've already defined that, of this function. So the function is actually a perfect straight line. They won't always be. And we're going to use left endpoint approximation. Okay? So, and we want 6 rectangles of equal width. That's really important. So first of all, you got to figure out how big your interval is. And so your interval is from 1 to 4. So it's a change of 3, but I want to split it into 6 intervals. So notice each interval is going to have to be half wide. Okay, so that's kind of nice because remember, the area of these rectangles are just the width times the height. So now we know the width, and now we have to figure out the height. So if we want the left end, think about it. That first rectangle is going to have a height right at 1. So we can get that literally by plugging in 1. Okay, then my next rectangle, since I'm only going to go over by a half, is going to have a height of, or is going to be at the x value of 1.5, because again, I would go my next interval. And then I'm at 2, and then I'm at 2.5. I think you get the idea. Oops, I did 2 of those. 2.5. I'm at a height of 3, 3.5, and then a height of 4. And the nice thing about these is they all are going to have an equal width. So all of these basically just get multiplied by 1/2, and that will give me the area of my rectangle. Now, some people, when the widths are equal, just take this whole string of numbers and multiply it by 1/2. So you could do that, or you could multiply each of these by 1/2 because this is the width and that's the height. When you do that, I got an area of 10.5. So let's take a look at one, for example, 2, that's a right endpoint approximation. So here's a nice example of something that's more curved. We've got x squared. We're going from 0 to 3, and we want 3 rectangles. So if we want to find our change in x width, well, our x has changed from 0 to 3, so we're going to find the difference there. So we're going to always take that bigger value minus the smaller, and we want to split it into 3. So this one's nice because this just comes out to a change of 1. So that means I'm going to stop at each value going up by ones. But because I'm doing a right end approximation, I'm not plugging in 0. I'm plugging in that first width. So I have to go from my beginning, which is 0, all the way over to 1. So I'm going to plug in 1, I'm going to plug in 2, and I'm going to plug in 3. Again, those are going to be those heights of the rectangles on the right side. How much is the width of each rectangle? Right here, 1. So basically, once again, I'm multiplying each of these by the width by 1. You can do it individually or you could put it out if it's equal. And so when I do that and I actually get those values, again, you can just plug them in here, guys. So like f of 1 is 1 squared is 1. F of 2 is 4. F of 3 is 9. I add those up, multiply them by 1, and I get 14. So that's how I'm getting that value. I'm actually plugging it in. Example 3, we'll use the midpoint approximation. So the midpoint, well, there's 2 minus 0 distance of my interval. I'm going to divide that by 4, and I end up with a difference of 1/2. So my change in x, or my width of my rectangles, should move by 1/2. Now, but here's the interesting thing. So I'm going to go through and mark those. So that would be 1/2 would be my first one, then 1, then 2, then 1.5 or 1.5, and then 2. Now, because I want the midpoint, I actually have to plug in what's in between that. So I have to actually plug in halfway between 0 and 1/2. So I'm actually going to plug in a fourth, or 0.25. My next rectangle is going to be perfectly in between here because I'm plugging in the midpoint, which is 0.75. Then I'm plugging in, I think you get the idea here, my next midpoint, which is at 1.25, and then my next midpoint, which is at 1.75. So I'm trying to find the height of the rectangle based on that halfway point. Now, the width of each of these, again, they're equal, and we already know they're 1/2, so I'm basically adding all of this together and multiplying each of those by 1/2. And so I end up with 8.5. Remember, the way that I'm getting that is I'm literally plugging in 0.25 up here into my equation. So I'll show you that first one. If I take half times f of 0.25 only, I get half of 6 minus 2 times 0.25. This is 6 minus 0.5 times 1/2, or half of 5.5. If I was going to do this by hand, I would do them as fractions. And so that's 11 halves. And so I end up with 11 fourths. So that's kind of nasty. But overall, once you get all of these and add them up, you do get 8.5. You can use your calculator for this. Okay, so let's do the trapezoidal approximation for this one. Remember that our trapezoids, this is x squared minus 1. It's going to look something kind of like this. But remember that our trapezoids have their height is actually this change in x, guys. So again, area of a trapezoid is 1/2 height times base 1 plus base 2. So it's the average of the heights. So that would mean we want 4 equal widths. So that's nice. I have an interval of 4. So my change in x, the difference here is 4. And I want four equal trapezoids. So that means each one is going to have a width of 1, or a height. In this case, remember, trapezoids would look like this, of 1. Okay, so this is kind of interesting. If you think about it, if I was finding my heights here, or my bases, excuse me, because remember, now these values are going to be your bases. I would do 1/2 height times base. So we already know that the height is going to stay 1 for all of them. So now we just have to figure out what our values are. Well, the first one is at 0, so f of 0. My next one, this end, is going to be at f of 1. Those are my two base 1 plus base 2s. Do you see that? That's my first set. My next set is going to be these two, which once again are 1 and 2 now. Okay, so that's those two sides. Now I'm going to do those two. Those are 2 and 3. And I think what you start to notice, my last set is 3 and 4. What you should notice is that I have repeats. In fact, all of them repeat except the very end. So technically, I could simplify it by multiplying those inner guys by 2. Again, the only ones that don't get repeated are the very outer values, so 0 and 4. And then I end up taking half of that, and that ends up being 18. Again, this is all, you're welcome to do this on the calculator, because again, f of 0, you'd plug it in, 0 squared minus 1, that'd be a negative 1. This is 2 times f of 1, you'd plug in 1, you'd get 0. So again, you're welcome to be using your calculators for those, but you can do them by hand. All right, for 5, we've got an actual data set of values. We want to do left-hand sums. We want to do 4 subintervals. We have 4 subintervals. It's important to see what the width is here because we can do different widths, which you guys are going to see in a second. So once again, the widths here all come out to 1. So since it's an even width, I can just keep that width out front and then just multiply by all the heights. So my first height is 20. My second height is 18. Because remember, this is like f of 2, 17, and 11. Now, because I'm doing the left-hand sum, I only need those guys. I wouldn't need this last one on the end. And this ends up being 66 for my area. For this one, I've got a midpoint sum. Now, this is interesting. Pay close attention to the directions. You want 3 subintervals from -1 to 2. So the difference here is 3. So technically, I'd be doing my subintervals by 1, which is why this chart gave you the midpoint. How nice was that? So you didn't have to figure it out because you don't have the equation. So again, if I was doing my rectangles, they're each a width of 1, so that's nice. And then I can just do what I get when I plug in the midpoints. So when I plug in this midpoint, the first one I get 30. The second midpoint is this guy in between, I get 19. And the last one here is 15 for a total of 64. Okay, and I believe this is our last example. So this one is a trapezoidal rule. So you know you're doing the 1/2 base times height. Now this is interesting. Check it out. They want 3 subintervals from 0 to 8. If your chart only gives you 3 intervals, you can use those 3, but they're going to have different heights. And by heights, again, I mean the width. Remember, that's the height there between these two. So on the first one, I'm going to use my formula for a trapezoid, which is 1/2 times the height. Now, the height between my first two is actually 3, the distance there. My base 1 and base 2 are what I get when I plug those values in. For the second interval, I have a height or a width of 1, and my base 1 and base 2 are 5 and 7, what I get when I plug in those. And for my last interval, I have a width of 4, and my base 1 and base 2 are 7 and 11. And when I add all that up, I get 52.5. So these get pretty interesting. We will definitely be practicing them in class, and we're going to do a lot more with this. This is a really foundational part for the second half of Unit 4. So enjoy the problem sets, and I'll see you.